The James Webb Telescope has now delivered another picture that shows something is truly amiss with our universe. All things considered, our space is going off the deep end, which would mean it has a knowledge of some sort, or our researchers absolutely got it wrong. The truth is that since the send-off of the new telescope, we are encountering an emergency in world science, any semblance of which we have never seen before. It appears as though the new discoveries are attempting to tell us something pressing. However, up to this point, researchers are contending beyond what they can present us with genuine facts and insights. Does this spell almost certain doom for all that? No stone has been left unturned since the JWST showed us pictures of systems that are so old and thus amazing that they shouldn't even exist. This was the start of a show in present-day science that continues to the present day. An ever-increasing number of pictures show considerably more insane peculiarities and difficulties. Nothing in the youthful universe is the manner in which researchers thought it would be, and presently, obviously, the whole universe isn't the way our researchers figured it would be. As of not long ago, analysts have assumed that the universe is homogeneous, meaning that its huge designs are to a great extent uniform in shape. Yet now, there are many signs that the universe is, in fact, inhomogeneous, and this calls into question a portion of the fundamental suppositions about the nature of the universe. The thought of a homogeneous universe goes back to the cosmology of the mid-20th century. Albert Einstein presented the cosmological constant in his general theory of relativity, describing a static universe that neither grows nor shrinks. A little later, it turned out to be clear that we don't live in a static universe. Rather, this space, with all its peculiarities, is profoundly dynamic. There is nothing that doesn't move in this universe. Anyway, the physicist Alexander Friedmann arrived at the resolution that Einstein's field conditions also work with a growing or contracting universe. Georges Lemaitre then proposed the possibility of the Big Bang, wherein the universe extended from a single point. These improvements led to the idea of a homogeneous and isotropic universe, which is anchored in the so-called cosmological principle. This principle states that the universe is homogeneous and isotropic on large scales, meaning that it looks the same everywhere, no matter where you look. We should contrast this with a scene. A homogeneous and isotropic scene would resemble a tremendous, unending desert in which the sand is equally distributed everywhere, without any hills, valleys, or other topographical features. Regardless of which direction you look or where you head, the scene looks the same everywhere. What's more, there are no preferred or special places. In the case of the universe, this would imply that stars, systems, galactic nebulae, and other peculiarities are all uniformly distributed in space. Anyway, recent revelations by the James Webb Space Telescope and other galactic observations have shown that the universe may not be as homogeneous and isotropic as previously suspected. The quasar and the Great Ring demonstrate it. It might be peculiar to envision the whole universe as a scene, but on closer review, this idea isn't entirely implausible. Just the scales are rather larger. Here we have galaxies with millions or billions of stars that wander around the universe along filaments and come together in clusters. We are aware of massive voids, black holes, and other peculiarities. All these objects participate in the cosmic display. Researchers have now found that one side of the sky has around 0.5% more quasars than the other side. Quasars are very bright cosmic cores fueled by exceptionally massive black holes. This lopsided distribution further suggests that matter in the universe isn't evenly distributed. Later, two incredibly large cosmic structures, the Great Ring and the Giant Arc, challenged the hypothesis of a homogeneous and isotropic universe. These structures, formed by galaxies and galaxy clusters, are so enormous that they exceed the scale on which the universe should be homogeneous and isotropic. Fundamentally, they are so huge that our measurement methods fail here. Such megastructures show that there are, at least, high mountains within the landscape of the universe, and no one currently knows how they have arisen or fit into the overall structure. Yet these are just the most recent discoveries that are gradually, but surely building up the doubt of a heterogeneous universe. Before these most recent exciting discoveries, there were already signs from the varying expansion rates of the universe. Various methods of measuring the expansion rate of the universe yielded different results. We know this contrast as the Hubble tension. If the universe isn't the same everywhere, this would explain why it isn't expanding consistently. Somewhere between the levels of the cosmic background radiation and the seeds, there could be a previously unknown layer of the universe or a force responsible for the measurement differences. Or the universe isn't expanding consistently because there is a massive obstacle somewhere in the way. Here, the new telescope has its part to play in current research, as researchers have utilized the James Webb Space Telescope to confirm the Hubble tension. Why does the cosmic background radiation show an even distribution of matter? Do you want to know a truly intriguing fact and an interesting hypothesis? Let's look again at the cosmic background radiation, or CMB for short. It does indeed show a uniform distribution of matter. The CMB is considered the remnant of the Big Bang and is essentially uniform microwave radiation. The radiation began at a time about 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine to form neutral hydrogen atoms. This moment is known as recombination. Before recombination, the universe was a hot, dense plasma of particles and electrons that constantly collided with one another and scattered photons. These constant interactions ensured that matter and radiation were closely coupled and in thermodynamic equilibrium. During this time, radiation was strongly scattered by the dense matter, preventing it from traveling significant distances without interacting with particles. As the universe continued to expand and cool, temperatures eventually dropped below around 3000 Kelvin, allowing electrons to combine with protons to form neutral hydrogen. This process drastically reduced the number of free electrons, making the universe transparent to photons. Light was finally able to travel unhindered, and the decoupling of matter and radiation continued. These released photons are what we now refer to as cosmic background radiation. It was the uniform distribution of CMB radiation that led researchers to believe that the universe was nearly homogeneous and isotropic over 13 billion years ago when it was smaller. But now, imagine if the universe isn't expanding in an empty space, but in a space where something already exists. The Big Bang and the distribution of matter right after might have been homogeneous, but then the expanding universe encountered obstacles that disrupted the homogeneity. These obstacles can be many things, but they all lead to intriguing speculations that captivate space enthusiasts and give researchers a headache. The old theory of the Big Bang states that space just came into being with a massive explosion. The expanding universe is space. According to old theories, there is nothing beyond this space. Quantum physics has already demonstrated that nothing can't exist, and quantum physics has shown that a multiverse with many settled aspects and countless universes of various shapes, sizes, and qualities is more likely than the one universe in which we live. So, what if our universe ventures into a space in which different universes, aspects, and previously unknown structures exist? This would obviously imply that it encounters obstacles, sends other universes or aspects away during its expansion, or they exert resistance on our universe. An initially homogeneous Big Bang would then become inhomogeneous because of these encounters. Such considerations are exciting, but despite the many anomalies in astronomy, they currently receive little official attention. Is our own Earth the proof? You might find it hard to believe, but some bold researchers who support theories like the multiverse have come up with an intriguing comparison. Our Earth too started as a homogeneous world. Planets in their early stages are accumulations of gas and dust, much like early stars are. Then they slowly develop and become more distinct, wandering around within the solar system, colliding with other celestial bodies, and changing. Initially, Earth was a blazing hot ball, and the matter was evenly distributed. Then a heterogeneous structure developed, at least on the surface. We have large oceans and land masses that are not evenly distributed across the globe, but rather more randomly. The Pacific is vast, just as the Eurasian continent is exceptionally large. Africa is directly adjacent, while the American continents are elongated and thin. We also have more heterogeneous structures within the oceans and on the continents, remote ocean trenches and channels, shallow areas, tidal pools, deserts, high mountains, densely populated areas, and sparsely populated regions have formed on the continents. But what can we gain from this inhomogeneity concerning the universe? Well, our Earth shows quite well that the planet has transformed over a long period from a homogeneous world into a heterogeneous one, at least to some degree. Essentially, the rocky planets all show signs of such changes. Mars, Venus, and Mercury also have heterogeneous structures, though not as extreme as on Earth. If we look at the rest of the solar system, the gas giants are homogeneous, with planets that have presumably barely changed their appearance over a long period. Yet, the variety of our planets alone again shows the uneven distribution of matter and gas within a planetary system. If we go back to the landscape of our universe, it is therefore quite possible that a universe takes on heterogeneous features throughout its development. The latest discoveries of the James Webb Space Telescope have shown that our science has been wrong in many ways. The old cosmology is breaking down, and we may now need to recognize that even physical forces undergo evolution and change over time. The James Webb Space Telescope, JWST, continues to redefine our understanding of the universe with each novel observation. Its extraordinary capabilities,